Hi children and viewers, this is N. Vinay Kumar. My channel name is N. Vinay Kumar Basics of Physics. Up to now you didn't subscribe my channel, then go and subscribe my channel for latest updates. Children and viewers, today's you are going to learn what is critical angle, what is total internal reflection, and what is use of total internal application in our daily life. So children, just we go to the topic now. Here today's topic is critical angle and total internal reflection, TIR. Today's topic is this only. Children, examination point of view and competitive exams point of view, very important and interesting topic. Before going to enter into the topic, first you have to check you have idea about these points or not. What is mean by reflection, what is mean by refraction, and what is mean by absolute refractive index and refractive index, and what is Snell's law. Just briefly we are going to those topics, and after that we will enter into the topic. Here now we know that this is the interface. When the light rays enter, for example, this is the medium 1 and this is the medium 2. Clear? Light is moving from medium 1 to medium 2. At this point there should be incident. At that point we are drawing one normal line. Then this is what we call angle of incidence. In that incident light, some of the light should be reflected and some of the light should be refracted. Clear? Now this is the angle of reflection, and now this is the angle of refraction. This is reflected ray and this is refracted ray. So this is the simple information about the reflection and refraction. Reflection means what? When the light is incident at any point of incidence on the interface, in that some portion of the light should be again going to the same medium. That is the reflection of light. And in that some portion of incident light that should be moving from one medium to the another medium, and at the point of incidence that should be deviates its path. That is what we call naturally refraction of light. When the light is moving from one medium to the another medium, here different mediums are having different velocity. That means the velocity of light varies from one medium to the another medium. When the light ray is moving from medium 1 to medium 2, the velocity will be changes. That's why the path of the light ray should be deviates. For example, here this is the one medium and from this another medium. When that should be enter into the next one, the medium will be changes. When the medium changes, velocity also changes. When velocity changes, its path of deviation also changes. So first thing, that is what this is about the reflection and refraction of light. Clear? And next thing here, what is mean by refractive index? Refractive index means it is the ability of the medium, how much it can be deviates the light ray, with what amount of force that should be deviates the path. That is the generally what we say refractive index. In some textbooks that should be shown with the mu, and in new textbooks that should be shown like n. Clear? Mu is refractive index, that is the property that should be represents the ability of the medium to deviate or to refract the light. That is the one property only here. Here we have one definition is there. What is absolute refractive index? Absolute refractive index means, just now only I told you, mu is equals to C by V. There C is the velocity of light in free space and V is the velocity of light in medium. Clear? velocity of light in free space or vacuum, and V is what? Velocity of light in particular medium. The ratio of these two should be gives the absolute refractive index. Absolute refractive index. Absolute refractive index is the ratio of velocity of light in free space to the velocity of light in medium. Clear, children? And tell me, guess, is there any units for this one? No units. Simply it is constant. Ratio of same quantities. It is a dimensionless quantity and unitless also. No units also. So here, this is the absolute refractive index. We are comparing now here one medium with the another. Here first we have some medium it is there, that should be compared with the vacuum. Now here I am writing now mu21 and mu12. Here what is mu21 and mu12? So to know that, mu21 means refractive index of second medium. Refractive index of second medium with respect to of first medium. That should be read like mu2 by mu1. Here mu21 represents what? Refractive index of the second medium with respect of first medium. Mu12 means what? Refractive index of first medium with respect to the second one. Refractive index of first medium with respect of second one. So that should be written as mu1 by mu2. Mu1 by mu2. So here mu is called absolute refractive index. Here mu12, mu21 is called refractive index. Refractive index of medium with respect of another medium. Clear? Now here we can derive the expression for it. So here what I am telling now here, mu is equals to C by V. Then what I can write, mu1 is equals to C by V1. 1 is the medium, 1 here. C by V1, velocity of medium, the first medium. And similarly, mu2 is equals to C by V2. Mu2 is equals to C by V2. So here C by V1, C by V2. Here C is the constant, 3 into 10 power of 8 meter per second. So from those two, what do you write? I am writing now mu1 by mu2. Mu1 by mu2 is equals to what, right? C by V1 by C by V2. What do you get? Mu1 by mu2 is equals to C by V1 into V2 by C. C cancel. What do you get? Mu1 by mu2 is equals to V2 by V1. Here, now that I write mu12. Mu12 is equals to mu1 by mu2 is equals to V2 by V1. Inversely proportional. Mu is proportional to 1 by V here. Mu1 by mu2 is equals to V2 by V1. That means here what you have to say, here V1, V2 means what? Velocity of light in first medium is the V1. Velocity of light in second medium is what? V2. We are comparing V1 and V2. By comparing the velocities in different medium, we can define the refractive index. This is mu12. What do you get? Mu1 by mu2 is equals to V2 by V1. If you can write mu2 V1, then what do you get? Mu2 by mu1 is equals to V1 by V2. So this is simply about the absolute refractive index and refractive index. Clear, children? Mu21, refractive index of second medium with respect of first one. Mu12, refractive index of first one with respect of second one. Okay, this is the basic information you must be understand about this one. And next thing is, we have one thing is there. Here we have some Snell's law. Snell's law. This also we are going to use. Snell's law. What is Snell's law? Clear? Snell's law means here nothing but mu21 is equals to sin I by sin R. Sin I by sin R. There I is the angle of incidence and R is the angle of refraction. Refraction. Clear? I is the angle of incidence and R is the angle of refraction. Clear? Now definition should be like this statement. the ratio of sine of angle of incidence to the sine of angle of refraction. Sine of angle of incidence to the sine of angle of refraction, that should be a constant. What's that? That should be a constant. That is mu to 1. That is what we call Snell's law. Clear, children? So we have to use all these things in now in this topic, critical angle and TIR. Clear? So first thing is here, what is critical angle and what is total internal reflection? For that, now one diagram it is there, very important question, children. Watch carefully. Now this is a medium 2 I am taking now. This is the medium 2 and this is the medium 1. Clear? And medium 1 is we are taking now, that is denser medium. Denser medium. And this is a rarer medium. Clear, children? What is denser medium and what is rarer medium? The medium which has lesser density, that should be taken as rarer medium. The medium which has more density, that should be taken as denser medium. For example, we will go for water and air. Air is now rarer medium and water is denser medium. Again, air and glass. The light is coming from the air and that should be passes through the glass windows. Now glass is the here refractive index. Clear, children? So that's why here, just imagine we are taking the diagram now here. I already told you what's that. It is the interface. How we can find the angle of incidence? At the point of incidence, we have to draw one normal, and the angle between normal and incident ray is what we call angle of incidence. And if it is the refracted ray, now angle is what? R. That means with the help of the normal only we can find the angle of incidence and angle of refraction. Don't forget that. So here now, what is Snell's law? Mu is equals to sin I by sin R. Mu is equals to sin I by sin R. So here now, this is the source. What is that? Source of light in denser medium. Source of light in denser medium. Clear? So here from that source one light ray is coming. I am saying that that light ray is here O and this is A. O, A. And so tell me here, either it is refracted or not. No, that should be against in the path of same. There is no change in its path here in this case. Simply again that should be going straight. While the light ray is moving from one medium to another medium, what do you have to observe? There is some change in velocity. When there is any change in velocity, the path of the light should be changes. But here no change. Why? Because to find out the angle of incidence and to find out the angle of refraction, you must use one normal. At this point, if you can draw normal, then this incident ray and refracted ray is parallel to the normal. Just I am drawing side. Just if I am taking now, this is the normal. How this seems to be? Yes, both are in parallel. When they are in parallel, what is the angle? 0 only. That's why here angle of incidence is 0 and angle of refraction also 0. Because here according to Snell's law, what you have to say? Mu is equals to sin I by sin R. What I am telling here, mu is constant. When mu is constant, what you have to write? Sin I is proportional to sin R. Sin I is proportional to sin R. Angle of incidence is directly proportional to the angle of refraction. When I is small, R also small. When I increases, R also increases. When I becomes maximum, R also maximum. Like that. So here, for the first ray, I am saying O, A is the incident ray and OA is the refracted ray without any deviation. Clear? A dash. Next thing is, here I am taking the another light ray, that is I am saying here, that is OB. OB is the another ray. Clear? Tell me here, the light is moving from which medium to which medium? Denser medium to the rarer medium. Clear, children? So here at this point I am drawing now here, this is B, I am taking here. Look here, at this point here normal is there and some angle of incidence is there. That means what? Angle of incidence is increase. Initially 0. Clear? And you have to notice one thing. This is the interface. When the light is coming from a rarer medium, this is what? Rarer medium. And this is what? Denser medium. At the point of incidence, I am drawing here one normal. When the light is coming from rarer medium to denser medium, the refracted ray is moving towards normal. Very important one. The light is coming from rarer medium. Clear? And that should be after refraction, it is moving towards. That means what? This is angle of incidence and this is angle of reflection. That means here angle of R is less than angle of I. When a light ray is moving from rarer medium to the denser medium, after refraction the light ray must be moves towards normal. Why? Because angle of refraction is less than angle of incidence. Clear, children? Angle of refraction must be less than the angle of incidence. Clear? And now here, this is related to our topic now here. Now this is what? Denser medium and this is what? Rarer medium. Again light ray is coming. That should be incident at this point. Clear? Now this is the normal. After refraction, the light ray is moving away from normal. Moving away from normal. That means what you have to say here? Angle of R is greater than angle of I. Angle of R is greater than angle of I. Children, clear? That means you have to remind now here. When the light is moving from denser medium to the rarer medium, it is moving away from normal. That's why in this case also here the ray is moving from denser medium to the rarer medium. That's why it is moving away from normal. Clear? So now this is the R. And after that B dash. So this is the B dash is the refracted ray. Next again we are increasing the angle of incidence. Again that should be having some angle of R also increases. Clear? Now I am taking, this is OB, D I am taking here. OB is the incident ray and BB dash is the refracted ray, and OD is the incident ray and OD dash is also refracted ray. After that you have to observe now here. It is the very crucial point. Clearly you can observe. And next I am taking the one more light ray. Clear? In this case the refracted rays grays along the interface. That means the light ray is refracted, but that should be inside the rarer medium, that should be moving along the interface. That is enter into the another medium. It is moving from denser to rarer. That is enter into the rarer, but that should be grays along the. For example, this is the interface. This is the light ray. Just now below this one denser medium. and this is the rarer medium. That should be entered and that should be moving like this. This is interface. On interface, that should be moving like this. Below denser and this is rarer. So then here that should be having some angle of refraction is here 90 degrees. 90 degrees. I am taking that light ray is OE and this is OE dash now. Clear? Now the angle of refraction is 90 degrees. For that the angle of incidence is there. That should be called here critical angle. What do you observe? Critical angle. From that, how we can define the critical angle? When the light ray is moving from denser medium to the rarer medium, for which angle of incidence, angle of refraction becomes 90 degrees. Then that particular angle of incidence is called critical angle. Got my point? The light is moving from where to where? Denser medium to the rarer medium. For which angle of incidence, angle of refraction becomes 90 degrees. So many people can confused. I observed so many students. They will mention angle of critical angle is 90. Critical angle is not 90. Angle of refraction is 90. I observed so many students. Here critical angle means for which angle of incidence, angle of refraction is 90. This 90 is not critical angle here. For this is the angle of refraction. Where we are getting the angle 90, for that angle of incidence is critical angle. Got children? Very simple. When the light is moving from denser medium to the rarer medium, for which angle of incidence, angle of refraction is becomes 90. That is what we call critical angle. So now this is what critical angle. Critical angle. After that, here we are taking one more light ray. One more light ray. That is I am taking OF. OF. Again we have to find the angle. So here the angle of incidence is more than the critical angle. Then so that means what? Here what do you observe? In the figure, angle is 0, angle is increased, further increased, for again we reach some critical angle. After the critical angle, again you can increase. Again you can increase the furtherly you can increase the angle of incidence more than the critical angle. Then the ray is totally reflected back into the same medium. The ray is totally reflected back into the same medium. That phenomena is called total internal reflection. What we call? Total internal reflection. Clear? When, watch carefully and listen carefully. When the light is moving from denser medium to the rarer medium, if the angle of incidence is more than the critical angle, then the rays are totally reflected back into the same denser medium. That phenomena what we call total internal reflection. So children, this is about the critical angle and total internal reflection. Clear children? So I will briefly explain again. Please listen carefully. Critical angle means when the light is moving from denser medium to the rarer medium, for which angle of incidence, angle of refraction becomes 90 degrees. That is what we call critical angle. Critical angle always must be shown by the symbol C. Clear children? And what is TIR? For critical total internal reflection, two conditions must be there. First one is what? 2 marks important question. What are the conditions to get light should be total internal reflection? The first condition is what? The light must be moved from denser medium to the rarer medium. First condition. Second thing is what? the angle of incidence must be greater than the critical angle. That is the second condition. So when the light is moving from denser medium to the rarer medium, if the angle of incidence is more than the critical angle, then the light should be totally reflected back into the same medium. That phenomena what we call total internal reflection. So these two must be explained with one diagram that should be here. In this figure, this should be taken as denser medium and it should be taken as rarer medium. One source is there. From that source we are getting so many light rays. We have to assume that so many light rays are coming with different type of angles. And now here the first ray is no deviation for it, because according to Snell's law we are writing sin I proportional to sin R. When I is 0, R also 0. And after that, what you observe here in this diagram, you have to observe that the light is moving from denser medium to the rarer medium. While you are drawing the diagram, you must take the refracted rays away from the normal. When the light is moving from denser to rarer, the light should be away from normal. You have to mention that. If you can keep like this, that's the wrong. Clear? All the rays should be moves away from the normal. In this figure, what you observe, if you can I value increase, R also increase, that should be shown in these two diagrams, two rays. And after that, for the ray OE, what you observe, the angle of refraction is 90 degrees. So for light ray OE, the angle of refraction is 90 degrees. Then here this particular angle of incidence, clear, 90 is not critical angle, only the angle of where we are getting the 90, for that particular angle of incidence is there, that should be taken as critical angle. And after that, you have to notice that further we are taking one more light ray that should be having angle of incidence is more than the critical angle. I am mentioning here, this is the F, but here I am mentioning I is greater than C. This is also I is equals to here, and here now I is greater than C, more than the critical angle. Then the ray is completely coming back. It does not enter into the rarer medium. The should comes back. So in this way, now it is what we call, this phenomena is the ray is completely back into the denser medium. That phenomena what we call total internal reflection. Children, this is about the information about the critical angle and total internal reflection. So next thing we have, for competitive exam purpose, there is some relation between refractive index and critical angle. We can, if you know about the critical angle value, we can easily find out the refractive index of particular medium. For that we have one relation, it is there. I am writing here. Here now, mu2 is equals to what, right? Sin I by sin R. mu2 is equals to what, right? Sin I by sin R. Here mu2 means what here? mu2 by mu1 is equals to sin I by sin R. Clear? Refractive index of second medium with respect of first medium. That is what we write, mu2 by mu1 is equals to sin I by sin R. Tell me now here, at critical angle, instead of I, what you have to write? C, as I is equals to C. And what is angle of R? 90. So R is equals to 90 degrees. So you have to substitute there. mu2 by mu1 is equals to sin C by sin 90. What is that? mu2 by mu1 is equals to sin C by sin 90. Sin 90 value is how much? 1. Look here. mu2 by mu1 is equals to sin C by 90 means 1. So then what do you get? mu2 by mu1 is equals to sin C. Here what is mu2? Refractive index of air. So for air, mu2 is equals to 1. mu2 is equals to 1. Then I am writing here 1 by mu1 is equals to sin C. 1 by mu1 is equals to sin C. So here I am taking now what is mu1, density of, refractive index of denser medium. So I am let mu1 is equals to mu. Then what do you write? 1 by mu is equals to sin C. 1 by mu is equals to sin C, and it is also mentioned like this: mu is equals to 1 by sin C. Mu is equals to 1 by sin C. So this is the relation between refractive index of the medium to the critical angle. So from this formula, mu is equals to 1 by C sin C. This is the relation between refractive index of the medium to the critical angle. If you know about the critical angle, we will find out the refractive index. If you know about the refractive index, we will find the critical angle. So maximum, if you know about the critical angle, we can find out the refractive index. So in competitive exams, NEET, so IIT, in that also we'll get some problems on these questions. So see once again, relation between mu and C. For that we are taking now here Snell's law. Mu2 1 is equals to sin I by sin R, and mu2 1 means what? Refractive index of second medium with respect of first medium, sin I by sin R. So we want to derive the relation between mu and C. C means what? Critical angle. At critical angle, that's why I am taking this situation now here. At critical angle, I value is what? C, and R value is what? 90. We are substituting mu2 by mu1 is equals to sin C by sin 90. So here sin 90 means what? 1. That's why what we get? Mu2 by mu1 is equals to sin C. Here what is the mu2? Mu1 is the refractive index of denser medium, and mu2 is rarer medium. I am taking now rarer medium is nothing but air. For that, mu2 value is 1. That's why we can substitute there. Then what do we get? 1 by mu1 is equals to sin C. Instead of mu1, I am writing now let mu1 is equals to mu. Then what do we get? 1 by mu is equals to sin C. Then mu is equals to 1 by sin C. So children, so this is the relation between refractive index of medium to the critical angle. Okay, so this is about the information about the critical angle and TIR. So now we go for applications of TIR, total internal reflection. Tell me how many conditions for TIR? 2 conditions. What is the first one? The light is must be moving from denser medium to the rarer medium. That is the first one. And next one is what? Yes, the angle of incidence must be greater than the critical angle. So here now, the first application in our daily life is formation of mirages. Formation of mirages. And brilliance of diamond. That means glowing or brightness of the diamond. And third one is optical fiber. Working of optical fiber. So in our daily life also, this situation what I am telling now, you also experienced, I think so. In summer, during the noon time, afternoon time, we are traveling in a car or any vehicle. While we are moving in the car, just you look at the road at some far distance, you may feel that some water traces may be to be appear. But after when we go to that place, we can't find any water traces. Again you can see that again some far distance, you can feel that some water trace will be there. So it is an optical illusion. So formation of mirages also same thing. So mirages means what we say in Telugu and Maulu, I think so. So that's why here formation of mirages is an optical illusion. Just we have thinking like that, but it is not true in fact. So here the reason behind what it is, got my point. While we are traveling along the road during the summer time on damper roads, we can feel that by looking at the roads some water traces will be there. While we went to there, but we can't find any water traces. So this is because of that is the same reason for formation of mirages also. Clear? So let us, what is the phenomena involved there? Let's we have check. Listen carefully here. This is the road surface or earth surface, anything. Clear? Here some air layers are there. Air layers. Just imagine the air layers should be divided into two types here. The layers which are very close to the earth and which are far away from that one, earth surface. So here we are taking now, just these layers are very close to the earth surface and these layers are very far off the earth surface. We know that when density is more, if the density of the medium is more, refractive index of the medium also more. When temperature is more, density is less and refractive index also less. That means temperature and refractive index both are inversely proportional. The refractive index is more means what? The temperature is less. Clear? Keep it in mind. Temperature, when temperature is more, density is less. When density is less, refractive index also less. When temperature is less, density is more. When density is more, refractive index also more. Got my point? The same thing applicable in this case. Here now, the air layers which are very close. For example, here, just imagine these layers are very close to the earth. We know that earth maybe gets heated fastly and cooled very fastly compared to the water. That's why when sunlight is falling on the earth surface, the sunlight absorbs the light. That's why earth gets heated. The air layers which are in contact with the earth surface, they also may get heated. Clear? Earth is heating only because of sunlight, by absorption of sunlight. Due to that, the temperature of earth surface will be increased, and the layers which are in contact with the earth surface, they may be gets heated. That means they becomes less denser. When density is less, refractive index also less. While we are going from here to in upward direction, density increases. Here density is increases. While we are coming from top to here, density is decreases. Clear? What I am telling? The layers which are in contact with the earth surface, they may be gets heated. They have more temperature. That's why here in this region you have to conclude they should be having less density and less refractive index. And now this layer or these layers are far away from the earth surface. That's why they have less temperature. That's why density is more. When density is more, refractive index also more. That's why, just imagine now, I am taking now, this is the line, interface. What's that? That is the interface. Now here sun is there. Just imagine the light rays are coming from like this. So it is coming from denser medium. It is more denser. That's why almost all this is the denser medium, and that should be having a rarer medium. Why? Because it have low density. Clear? So up to now what we discussed, when the light is moving from denser medium to rarer medium, if the angle of incidence is more than the critical angle, that should be completely reflected back. The light rays which are coming from the denser medium to the rarer medium, if they have angle of incidence is more than critical angle, they should be completely reflected back. That's why these are very close. Just imagine why we are getting image of, we can feel that some water trace is there. Why? Because when we are far away from that place, we can seems that the light is coming and that should be goes back. That's why we can feel that is very shiny place, very brightful there. That means here what we say, we seems that generally it is quite similar to the when the sunlight is falling on water surface, it's how it seems to be very bright. In the same manner here also that should be like that. So that's why it is an optical illusion to us. There is some water will be there. That's why this is the reason the atmospheres, the layers of atmosphere have different densities. Which are at the top they have more density, and which are at the bottom are very near to the earth, they have lesser density. While it is coming from higher density to the lower density, they should be completely reflected back. This is the reason behind why we can feel that some water trace on the road, and why the formation of mirages in deserts. So the one textbook example is given in our textbook. So see that once here. The same phenomena involved there. Same to same. Here it is the one big tree, tall tree. Here is a person. So when there is no hot breezes near the earth, nearer to the earth, it can feel quite natural. It seems to be, it is like tree only that should be erected. He was not finding any difference. But when there is some hotter air nearer to the earth surface, he can feel that the tree seems to be like this. Because of it's an optical illusion. Because of total internal reflection, you may feel like that. So in our textbook with diagrams it is very clear. So after this, watching this video, once you go through that, we can easily understand that example. So this is the first application to formation of mirages. What is the reason there? Total internal reflection. And next thing is we have second thing. So brilliance of diamond. Brilliance of diamond means the diamond seems to be very brightful. So very shiny. Why? Because same thing here. Just imagine. Just I am going to draw some diamond. It is some diamond like this. So just imagine. It's a diamond. Diamond laundry. Okay. So it's a diamond. Clear. The light is entered. This is the first surface. Light is entered. Then this light ray is refracted. Clear. For this surface, this is the incident ray, and now it is the refracted ray. Just you can go for it now. Now it seems to be incident ray for second surface. So it is now incident ray for this surface. While it was incident at this position, if you can draw normal, that should be having some angle of incidence is greater than critical angle. For a diamond, that should be almost all, I think so, 24.4 degrees. That should be having some like this. Then that should be totally reflected. And again same thing, here also having some angle, same angle, then again that should be reflected. So that means what? Once a light ray is entered into the diamond, that should be, once a light ray is entered with an angle 24.4 degrees, that should be going under in multiple reflections inside the diamond. After reflections only, that should be going back. That's why the diamond seems to be very brilliant or very bright. So that means what? Here again that should be completely going back. Here what you have to say? This is the air and this is the diamond. rarer medium, and this is now denser medium. That means from inside means what? It is a denser. Again it wants to come. Again wants to come. Denser medium to the, it is rarer medium, it is coming. Again if the angle is more than the critical angle, now it is going back. Diamond is the denser medium here, air is the rarer medium. Light is coming from here, denser medium to the rarer medium. If the angle of incidence is more than critical angle, again going to the back. Got children? So in this way the diamond is very very brightful and brilliant. And now third one, it is also very easiest thing, same phenomena here also. Working of optical fiber. Optical fiber. What is an optical fiber? Optical fiber is a device that can transmit the light energy from one place to another. It is the device that can transfer light energy from one place to the another place without losing of any energy. Without loss of energy, there should be transfers energy from one place to the another place. That is what we call optical fiber. So generally the optical fiber should be having like this. It is the core. That should be called cladding, and above that we have some buffer or shielding, you can say. This is core, this is cladding, and it is what? Core. Core only can transfer the energy, and now this is a shielding or buffer. Shielding means giving protection to the cladding. So here core only can transfer the energy. Just you can go and see the dish cable. Inside we have a line. In our houses we have some cable connection wires are there. From that, if you can open it, above we have some black color. Next one what you have some white color. Inside that one what you have some copper wire. So here copper wire is nothing but core. White is called here shielding, cladding, and black is what we call buffer. So here this optical fiber also working on the principle of total internal reflection. So just we have to go for that. Now this is the core, and this is cladding, and this is shielding. Clear? So I am showing that this is the buffer. I am showing like this. Clear? And this is the cladding. Just to identify them, I am giving the notifications like this. Clear? Now this is the core, and this one is cladding, and this one is shield or buffer. Clear? So now core only can transfer the energy from one place to the another place without any loss. Clear? Now this is the surface. Starting here, one ray is entered. One ray should be entered. So that should be refracted. At this point or at this surface, this is the incident ray, and now this is the refracted ray. Again same thing, this is the refracted ray for this surface. That means we are sending some signals like this. The signal should be entered like this and that should be refracted. This refracted ray becomes at this point incident ray, and that should be incident with some critical angle. That's why that is reflected back. Again same thing. Here also angle of incidence is more than the critical angle. That should be reflected. The same phenomena up to last. That means what? Very simple. This is the starting place of core. We are sending some light ray or signal. This is the signal what we sent. Then the signal should be refracted. That is entered and that should be incident at a point on the core. At that point, the refracted ray is having some angle more than the angle of incidence. That's why that should be reflected. Here you have to notice that the core is having more density. Core is having more density than the cladding. That's why here this ray wants to go to the from denser medium to the rarer medium, but it's not possible because the cladding is not supposed to move. The cladding purpose is it does not allow the light through them. That's why here the angle must be here more than the critical angle. Due to this only the light is reflected back. At every point that wants to go outside, but here now it is the denser medium and this is the rarer medium. At every point what I have to say, the angle of incidence is more than the critical angle. That's why the light should be reflected back. So due to the number of multiple reflections, the energy should be transferred from one place to the another place. So in this case also phenomena of what? Total internal reflection. So in this way the optical fibers may be used in so many ways. Doctors also, they want to see the internal organs which are in our stomach by sending the optical fibers into the stomach, and they want to see so many internal organs with the help of optical fibers only. Clear? So in different ways we can use the optical fibers in nowadays. So these are the applications of total internal reflections. Children, I hope all of you understand what about the critical angle, total internal reflection, how the formation of mirages. So I think all of you understand. After watching this video, just go for your textbook and see the examples. You will understand very clearly for a long time. So children, for a long time you must be remember this topic, I think so. If you can understand this topic, like and share in my video. Please subscribe my channel. Children, we will meet in the next video with a different topic, again new topic. So keep subscribe my channel for the next updates. We will meet in the next video. Thank you.